So today we're going to be looking at titrations and pH curves of strong acids and strong bases. Okay, so generically speaking, let's go ahead and let's look at the components of a titration. Okay, so basically in a titration, you're going to have some unknown substance, usually an acid or a base, okay, that's being titrated with a solution of known concentration. So if I have an acid down here, I'm going to have a base up here, and vice versa. If I have a base down here, I'll have an acid up here. Now, your titrant is the substance that you know the concentration of. So that's the thing that ends up being put in your burette and that you're measuring very precisely with that piece of equipment. So to the unknown solution, down in the Erlenmeyer, we typically also add something called an indicator. And so basically what an indicator is it's a substance that at a certain point, known as the endpoint, establishes a color change associated with a specific pH value. So basically, once you reach a certain pH value in this solution, you're going to have a color change associated with that point. Now, that's not to be confused with your equivalence point, which is the point at which the moles of your acid and your moles of your base are equal. Okay, so basically when you actually have titrated the solution. And typically you want to utilize an indicator down here that's going to have an endpoint that's very close to the equivalence point. Now, it's not always possible to get one that's directly on that value. However, depending on your acid-base combo that you have going on, you could kind of tweak that a little bit. And we'll look at the different types of indicators that are available. Okay, now, when we take a plot or make a plot of the pH of the solution versus the volume of the titrant that we've added, we get something called a pH or a titration curve. And the pH and titration curves are going to look very different depending on the type of titration that you do. So whether you use a strong combo of your acid and base, or you have a weak, strong combo, they're going to have different looks and different pieces of information that you can glean from them. So we're going to look at those details in a little bit here. Okay, so let's go ahead and let's look at strong titration. So basically what that means is that the titrant that's in your burette is strong, so your thing that you know the concentration of, and your unknown is going to be strong as well. Okay, so in strong titrations, really what you're doing in a kind of basic way, if we look at the net ionic equation of the acid and base reactive species, we have our acid putting H plus in a solution, our base putting OH minus. Okay, when they come together, we get a neutralization or the formation of H2O. Now, for strong titrations, the phenolphthalein indicator is the best option. Okay, and we're going to go ahead and look at a titration study of basically the titration of a solution of 0.200 molar nitric acid, which we know is a strong acid. So we're going to take 50 milliliters of that, and we're going to titrate that with a solution of 0.10 molar NaOH. And then we're going to subsequently look at the titration curve when we graph the volume of the base that we've added versus the pH change that are experienced. So we're going to kind of look at this data. Now, normally, guys, we wouldn't know the concentration of our acid that we have in the Erlenmeyer, okay, or the base if we were reversing the process. But in this situation, we're doing a case study so we can see the progression through the titration curve production. Okay, so notice on the right-hand side here, guys, we have this pH curve. Notice I have dots already established on the curve. So basically, your pH curve is going to look something like this. Now we're going to be looking at the individual points along this curve and basically how the values of pH that we get relate to the concentrations or the volumes of NaOH that we're actually adding. So before we start the titration, so point A, at this point we haven't added any NaOH. Remember, NaOH is the titrant that we're adding to the base, or sorry, to the Erlenmeyer that contains our nitric acid. Okay, so remember, the titrant is our NaOH, and our quote-unquote unknown, in this case we do know, is HNO3. So before any NaOH is added, Okay, all I have in solution is HNO3. Okay, and we know that HNO3 dissociates into H plus, NO3 minus, and H2O. So at this point, okay, at this point in the titration process, the pH is determined only by the concentration of the H plus from the strong acid that's in that Erlenmeyer. Okay, so we know the concentration of HNO3 is 0.200 molar, okay, and we know that since a strong acid dissociates completely into its corresponding ions, we subsequently know that H plus has the same concentration as HNO3, and if we take the negative log of that, we subsequently get our pH of that solution. So at a volume of 0 with respect to the NaOH added, our pH value is going to be 0.699, which makes sense to have a very low pH when we have a really strong acid in solution. Okay, so now let's move on to point B on the graph. So point B on this graph right here, okay, as you can see, is the point at which 10 milliliters of the 0.100 molar NaOH has been added. So at this point, we have our H plus, we have our HNO3 because we still, of course, have acid present, and of course the H2O. But now we've added some sodium and hydroxide ion solutions. Now we know that H plus and OH minus are going to come together to give us more H2O. So stoichiometrically speaking, H plus and OH minus are going to react to give you H2O. So really, the way we can kind of look at this process is that H plus is kind of being removed from solution, and basically we are putting something that's neutral, or more of something that's neutral, into solution. Okay, so if we look at this stoichiometrically, right, basically we look at the number of moles of each of our reactants that have been added, we see that we have 0.01 moles of H plus in that Erlenmeyer, and 0.001 moles of hydroxide that we have added into that Erlenmeyer. Okay, so these are the amounts that have been put into the container, and we know that H plus and OH minus are going to react in this one-to-one fashion. So after the addition of the hydroxide, we know that the amount of H plus is going to decrease, okay, and obviously the amount of OH minus is going to decrease. So my original amount of H plus was 0.01. So what I'm going to do is I'm going to subtract out that I'm going to subtract from 0.01 the 0.001 moles associated with the hydroxide, okay, and I've done that here, and that gives me 0.009 moles of H plus in solution, okay, and in that interaction between H plus and OH minus, obviously we've used up all of the hydroxide that's been added at that point. Okay, so after we've added that hydroxide, we know that the hydroxide all gets used up, okay, so we don't list them in the major species that are present, okay, but I still have that 0.009 moles of H plus present, okay, and of course I have the counter ions from the various acids and bases that are in solution, okay, so in order to figure out my pH, I need to determine how many H plus ions are left, okay, well, I already know that I have 0.009 moles of H plus left, I know the volume of solution, and I need to calculate that based on both the original volume of my acid plus whatever volume of base that I added. So in this case, I know I added 10 mils of that base to that 50 mils of NaOH. So notice I have a new total volume of 0.06 liters. Okay, so I divide my number of moles of H plus remaining by my new total volume. Okay, and that gives me my concentration of H plus. I then subsequently plug that into the pH equation by taking the negative log of that concentration, and that now gives me a pH of 0.82, okay, which is a little bit higher than what we saw in the initial phase when it was just acid by itself. So we still definitely have a whole bunch of acid left over. Okay, so that's point B. Okay, we're going to now go ahead and move on to point C on the graph. Okay, so point C on this graph here, at this point we've added 20 milliliters of the base. Okay, so just like we saw on the last slide, we have, our acid present, okay, we have our hydroxide present, and of course they're going to react in that stoichiometric way, that 1-to-1 ratio, to produce H2O. Okay, so at point C, we want to see what the pH value is. So before we do that, we need to figure out how much H plus gets used up by the hydroxide that's been added. Okay, so once again, we take our volume, or rather our amount of H plus that's present by taking the concentration of our original acid times the volume that's in the container. Okay, and we do the same thing for our hydroxide that we've added. In this case, we've added 20 milliliters. So, okay, obviously we're taking the additions from step B and step C and summing them together. We're not parsing them out. Okay, so basically what we're doing is we're figuring out how much hydroxide has been put into solution and how much it's going to, or how much H plus is going to be used in order to produce H2O. Okay, so once we figured out our molar amounts, we can then subtract out the amount of hydroxide ion that's going to interact with H plus from the original number of moles of H plus. And that subsequently gives us a little bit smaller value than we saw in the previous step. Okay, so in point B. All right, once again, all the hydroxide gets used up because we obviously still have a bunch of acid present in that container. Okay, and then what we're going to do is we're going to take these values and, this value and subsequently figure out the pH at that point. So if we go ahead and look at the concentration values, remember once again all the hydroxide ion got used up. We looked at the stoichiometry on the last slide. Okay, and we're going to once again determine the H plus concentration based on the moles of H plus left and divided by the new total volume of the solution that's in that Erlenmeyer flask. Okay, so 0.008 moles of H plus is what we calculated stoichiometrically. Our new volume of NaOH plus H plus volumes summed together is going to give us our total volume, and that gives us a new concentration of H plus. We take the negative log of that value just like we did and subsequently get an even higher pH. So notice as we decrease the number of hydrogens or H plus ions, protons in solution, notice that the pH curve is increasing. Okay, so that progression is going to continue. Now, also remember that when I'm making a titration curve, I'm comparing the volume of NaOH, or the titrant that's added, versus the pH. Okay, so at point C, obviously we've added 20 milliliters of the sodium hydroxide, and our pH has subsequently increased. Okay, so at point D, we're going to continue on the same approach we've been doing for the last several slides. We're looking at the stoichiometric relationship between the H plus from the HNO3 and the OH minus from the hydroxide ion that we've added. Okay, same approach. We get our number of moles. Okay, we subtract them out from one another, and we subsequently get our number of moles of H plus remaining. Okay, obviously the hydroxide ion gets all used up because we still have H plus in solution, and that subsequently brings us once again to the pH determining step. Okay, so once again, that pH determining step is going to be obviously dictated by the moles of H plus that are left in solution. We've already calculated that on the other table that we just looked on the last slide. Okay, we're going to take our total volume. Okay, once again, the amount of H plus and the amount of HNO3 volume and the volume of NaOH that's been added. We sum those two volumes together. Okay, divided into the moles of H plus left over. We get our new concentration, and we take the negative log to get our new pH. So notice now we have a pH of 1.3. Okay, at point B, once again, we've continued to increase our pH as we've added more hydroxide ion. Obviously, addition of hydroxide ion decreases the H plus concentration and subsequently changes your pH. Okay, so obviously this trend of, as you continue to add base, you're going to obviously continue to increase the pH. That's going to continue, and the titration curve is obviously going to look something like what we have here. Now, as we continue to add our NaOH, the pH changes are going to keep going, and eventually we're going to get to point E. Okay, so at point E, we have 100 milliliters of NaOH that's been added. Okay, so once again, we're going to look at our stoich, right? Our H plus and our OH minus coming together. Okay, we figure out those molar amounts. Okay, we subtract them out from each other. And notice at this point, we have 0 moles of either the H plus and the OH. So at this point, we've reached a special location on the titration curve. Okay, so this special location on the titration curve basically has H plus and OH minus being completely consumed. Okay, so what's going to be the determining factor for our pH in the solution? Well, the reality of it is that, the only species present that actually can affect pH or is going to dictate pH is going to be the H2O, right? We know that Na plus and NO3 minus are both the conjugates of strong component pieces, so they don't have a change in pH. So H2O is a determining factor. Okay, so we know that the concentration of H plus ion in water, right, is going to be 1 times 10 to the negative 7 at room temperature, so your pH is going to be 7. Okay, so for this strong titration curve, the point at which the number of hydroxide ions and the number of H plus ions are equal, that's called the equivalence point. And the equivalence point has this sharp curve that forms, okay, when we reach that point. Okay, so basically you're going to see this nice jump, okay, and basically the reaching of that pH equal to 7 is when those H plus and OH minus ions have basically canceled each other out. Okay, so at this point, H plus, OH minus are equal, okay, and you're going to expect that pH of 7 for this strong titration. Okay, now if we continue to titrate this solution, right, if we continue to go past the equivalence point, this is where we end up with points F and G. And so let's go ahead and look at those. Okay, so when I've added 150 milliliters of the NaOH, at this point, guys, realize that we're going beyond the H plus ion concentration. Okay, so let's go ahead and look at this. So we know that initially, obviously, if we just added 150 milliliters straight away, okay, initially we'd have this many moles of H plus. This is the number of moles of OH minus that we would be adding. Okay, so they interact in a one-to-one way. So what ends up happening is that, you know, as we saw at the equivalence point, the H plus and the OH minus reacted completely. Okay, so we subsequently ended up with 0 moles of H plus. However, remember, I've added an additional 50 milliliters of NaOH. So the reality of it is that I actually have some hydroxide ion left over when I go past this equivalence point, right? Because at the equivalence point, H plus is all used up. Past the equivalence point, at this point we're just adding additional hydroxide ions in solution. Okay, so now that I've gotten this hydroxide ion solution, or so hydroxide ion molar amount, I can figure out its concentration. Okay, so remember that your pH now that we've passed the equivalence point for this specific titration, is going to be based on the hydroxide ions remaining. Okay, so the moles of OH minus left over divided by the total volume of solution. Okay, notice I'm still considering the volume of acid that was added and the volume of NaOH that was added. Okay, I plug this into the negative POH, or sorry, the negative OH minus equaling POH calculation, and then I use the pH plus POH equals 14 calculation to subsequently get my pH of 12.4. Okay, so that's my point F. So notice, you know, you're creeping. Eventually you get a big change at the equivalence point, and then as you continue to add base, you're going to have a pretty stark increase in your pH value. Okay, and that should make sense to you because of the fact that as you're adding as you're adding base to that acid, you're using up the acid. Once you've used up that acid, the OH minus concentration is going to be, you know, a big factor in determining that pH value. So let's go ahead and look at the last point on the curve, the point at which we've done the 200 milliliters or added the 200 milliliters of NaOH to the solution. Okay, so we're basically looking at the end of that titration curve. Okay, we look at our original concentration of H plus, our total concentration of OH minus. We're figuring out the molar amounts. Okay, we know that at the equivalence point, the number of moles of H plus were used up. Okay, and this allows us here to figure out the amount of OH minus remaining in solution. So 0.01 moles is what we have. Okay, we can then take those values to figure out the concentration, just like we have over and over. Okay, so we take those moles of OH minus left, divided by the volume, just like we've done, we get a concentration of 0.04 molar. Okay, and then obviously we do our calculation just like we did before. We take our negative log of our OH minus, subtract that out from 14, and that's going to give us our pH of 12.61. Okay, so this is the titration curve that we end up with for this specific strong titration relationship. So remember, guys, the titrant, okay, was the NaOH, okay, and HNO3 was the acid being titrated. Okay, so this is a strong example, and this is subsequently the curve that you would anticipate when your titrant is the base, okay, and the thing that's being titrated is your acid. Okay, so some things to note, guys. We've talked about the fact that if we have the titrant being a strong base, okay, and our unknown being a strong acid, our curve is going to look like this, right? We start with an acid, so our pH here is going to start low, okay? Eventually it's going to increase as we continue to add base, and then once we go past the equivalence point, your pH is going to continue to increase because the hydroxide ion concentration is the main determining factor. Okay. Also, for strong situations, your equivalence point is going to be 7 because you produce water, and water has a pH of 7. Now, if our titration is reversed, and basically we're taking a strong acid as our titrant and our unknown is a strong base, it's a very similar curve to what we see on the left-hand side over here, but really what we've done is we've reversed the process. So notice we start up at a high pH, right, because we have a base down in that Erlenmeyer, okay, and as we add acid, we start to decrease the pH so that the solution becomes more acidic, okay. Notice though that the equivalence point is still going to be the same as over here, and that's because you're using strong components, so when those H plus and OH minus ions are equal, okay, remember for the strong situation, you're going to end up with H2O being the determining factor for your pH. Okay, so just make sure that you guys are paying attention to which is the titrant, so what's the thing in the burette, and what's the thing in the or what's the substance that's inside the Erlenmeyer down below, okay, and based on that you'll be able to establish which curve is appropriate. Also, making sure that you understand what types of acids you have, so strong is going to give you this type of curve set, okay, depending on which one is the titrant. So you need to pay attention to that, because as we move into weak strong situations for titration, there's some differences in the curves. So as I've said, guys, before the equivalence point, when you are titrating an unknown strong acid with a strong base, so your titrant is the base, before the equivalence point, you're going to be having lots of acid in solution because that's what's down here in the Erlenmeyer. Okay, so before the equivalence point, H plus is going to be the thing that determines your pH value. At the equivalence point, because you're adding a strong base, okay, that's going to end up being 7 because the H plus and the OH minus coming together neutralize one another. Okay, so that gives you H2O. H2O is present at that equivalence point, so that's a determining factor for pH at that point. And after that equivalence point, hydroxide ions remaining is what's going to determine the concentration and the subsequent pH of the solution. So make sure that you guys are calculating the OH minus that's actually remaining, okay? And remember that at the equivalence point, this is the point at which you have used up all of the acid. So beyond that, past that point, the rest will be just hydroxide ions remaining, okay? So now the opposite is true for when you're titrating an unknown strong base with a strong acid, so your titrant is the acid, right? That curve is going to look different. You're going to start up at a high pH, okay, so it's going to be determined by, before the equivalence point, it's going to be determined by the concentration of OH minus, okay, and after the equivalence point, it's going to be determined by the H plus. So make sure you're paying attention to what is the titrant, so that's the thing in the burette, okay, and obviously the thing that's being titrated. So what's the best indicator for strong titrations? Well, honestly, phenolphthalein is what's used most of the time. Methyl red is also another option. So with phenolphthalein, what happens is it remains clear at low pH. Okay, so if I add phenolphthalein to the titration that we just discussed, okay, what we're going to end up seeing is basically just a clear solution. As I continue to add NaOH to the solution, the amount of H plus present decreases, okay, and eventually as you get closer and closer to this equivalence point, what's going to happen is a pinkish color is going to start to show up. It'll show up, disappear, and once you've reached the equivalence point, a pale pink color will persist. Okay, so basically a good titration, when phenolphthalein is your indicator, ends up with a very, very soft, pale pink hue to the Erlenmeyer flask. Okay, now, as you go past the equivalence point, the pink color increases. You end up with a kind of a magenta color, and you subsequently have obviously gone past that equivalence point. Okay, if you're using methyl red instead, you'll start out at a solution that has a red color. As you approach the equivalence point, it'll turn orangish, and as you go past the equivalence point, it'll turn yellow. Methyl red is occasionally used, however, phenolphthalein is very, very commonly used. Both would be completely acceptable indicators for a titration. So one thing though you may be asking is, the color change expectations associated with, the methyl red or the phenolphthalein occur over a pretty large range. We're talking, basically around pH of 5 to up to past 10 in terms of those color changes. And, you may ask, well, how is that, acceptable in terms of utilizing these indicators to help us, figure out that equivalence point? Okay, and so let's talk about that. Okay, well, the reason why there's such a big range for these indicators is that the reality of it is that there's a very dramatic change in pH at the equivalence point. So basically, we want something that is going to be able to indicate, hey, pH is changing without a permanency associated with it. So we want that red color to start to dull, or we want that pink color to start to show up and go away before the equivalence point has been reached, right? Because we want a very sharp change, a sharp indicator that, hey, we are in fact at the equivalence point. So we don't want that to all of a sudden happen and we go way past that equivalence point. So basically we want that indicator to kind of give us a heads up that we're getting closer and closer to that equivalence point, and then we want a distinctive change at the equivalence point. So we want to go from that red color to that orange color, and we want that to be a clear indication that that equivalence point has occurred. But we also want kind of an indicator that, hey, it's coming up, it's going to happen. And we see this actually really nicely with the phenolphthalein indicator. We go from that clear solution, and what ends up happening is as we're adding that base, that pink color kind of stays longer and longer. So you swirl and get the pink to go away, but as it starts to linger longer and longer, we know that we're getting closer and closer to the equivalence point. And basically what ends up happening is you get to the point where you add one extra drop and you reach that point where that pink color is going to stay forever. So, there's a lot of choices for indicators to be used, but basically, depending on the situation, you're going to pick the indicator that you think is going to work best. However, as I said, the methyl red and the phenolphthalein are the best for strong. Here's a list of some indicators and their color and pH range change. Okay, you can see, yellowish color all the way to blue. And basically the range over which this pH change will actually happen. We got our phenolphthalein down here. Obviously we start with that clear and then move into that pinkish color, that nice pinkish color we want to have. And depending on what type of acids you're going to be using, or what type of bases you're going to be using and their subsequent pH values you'd anticipate, you could select from any of these. In this class we're not going to be using any other than the phenolphthalein. But just be aware that other indicators do in fact exist.